So resistance is same, it always opposes the flow of current, or it converts electrical energy into heat energy or light energy. The property of resistance does not change for AC and DC. It's the same. It's a time independent quantity. So the behavior of resistance is independent of time. It always opposes flow of current, or it converts electrical energy into heat energy. When it comes to the inductance properties, it opposes rate of change of current. Okay, so current is keep changing in AC, so inductor does not act like a short circuit similar to DC. In DC, once it is fully energized, inductor act like a short circuit. But when it comes to AC, it's no longer act like a short circuit, it acts like an inductor. It current is keep changing, it keeps opposing that change in current. Okay, so inductor is going to behave like an inductor. Now, so and here inductor is, it is a time dependent quantity. It is a time dependent quantity. Now if I have a resistor in series with inductor R and L, this is in ohm, this is in Henry, can we add them? We cannot add them when there are two different quantities. What I'm going to do here, I'm going to convert this time dependent quantity L into a time independent quantity. When I convert that into time independent quantity, we call that as inductive reactance. Inductive reactance. Inductive reactance is when inductance is converted into resistance. We call, so this is always, it is always imaginary quantity. Okay. So inductive reactance is nothing but it opposes flow of current. Oppose flow of current. Okay, now it is, once I convert the inductance into inductive reactance, it is time independent quantity. Okay, it is always imaginary quantity. We indicate with XL measured in ohm. Now for imaginary term we use I in mathematics, that's what we learned, but here I'm using I for current, so to avoid confusion I'm going to use J. We call it as either JXL or XLJ, IXL or XLI, everything is same. Okay, so this I and J indicates imaginary. Okay, don't get confused. So in future I'm going to use J instead of I because I'm already using I for current. So if I have a resistance and reactance, resistance and inductance in series, then I can convert this into ohms. So this is going to be R ohms, this is going to be JXL ohm. Okay, so JXL equal to J omega L, where omega equal to angular frequency in radians per second, or omega equal to 2 pi f. We always use, you need to remember this formula, we're going to use this a lot. So inductive reactance XL equal to omega L. Now capacitive reactance. Okay, so this before going to capacitive reactance, my apology, now I can combine these two because both of them are in ohms. We call this as R plus JXL. Okay, R plus JXL is called impedance. I will talk about impedance in a minute. Before that, I want to talk about capacitive reactance. Now capacitive reactance, it always opposes the flow of current in AC because capacitor, property of capacitor is it opposes rate of change of voltage, and voltage is changing all the time in AC. So capacitor is going to come into the picture, it always opposes that change. Okay, do you remember capacitor acts like open circuit in DC because that's a direct current once it is fully energized. But here when it comes to the AC, the voltage is keep changing, so it comes into the picture. Now I mean capacitance is in farad, but I cannot combine resistance with capacitance because this is in farad, this is in ohms. what I'm going to do, I'm going to convert this into ohms. When I convert this into ohms, we call that as capacitive reactance. Okay, so capacitive reactance, it opposes the flow of current in AC, and it is always imaginary quantity. It is a time dependent quantity. I mean, once I convert this into capacitive reactance, it's a time independent quantity. Okay, so one important thing is capacitive reactance is always a negative number, negative imaginary number, and inductive reactance is always positive imaginary number. That's you need to remember. Okay, so capacitive reactance is always a negative imaginary number, inductive reactance is always positive imaginary number. Now once we understand capacitive reactance, now I'm going to represent or introduce new term called impedance. We indicate with a Z. Impedance is nothing but it opposes flow of current in AC. Oppose flow of current in AC. Okay, so if you take an example, so this G is always either you will end up with R plus J XL, say for example that is 3 plus J4, or you might end up with R minus J XC. Okay, like 8 minus J6, something like this. These are all impedance. So impedance is nothing but a complex number. This is a complex number. Complex number definitely have a real quantity and imaginary quantity. So here I have real quantity and imaginary quantity. Now this complex number we can represent in two formats. Okay, those two formats are, one is called rectangular format. So Z equal to 3 plus J4, we call this as rectangular format, or we can represent this as 53.13, 5 at an angle of 53.13. This format is called polar format. Okay, so the impedance is a complex number. It has resistance and reactance. So usually you say R equal to plus or minus Jx. So it could be, if it is plus Jx, capacitive plus Jx, it is inductive reactance. If it is minus Jx, it's capacitive reactance. Okay, I will stop it here, and I will make a whole video based on the complex number. My next video is going to be based on the complex numbers, and I will tell you there how to convert rectangular to polar, polar to rectangular. Thank you.